Hello, sir. சார் வந்துட்டாரு, அவர் அன்மியூட் பண்ணியிருக்காரு, ஃபேஸ் தெரியுது, எங்களுக்கு ஏன் ஃபுல் ஸ்கிரீன் வர மாட்டேது? So good morning to all. I am Dr. A. Tyagarajan, Associate Professor, Department of Mechanical Engineering, Sri Manukala Engineering College. So a warm welcome you all for the ATAL FDP on Design Thinking, which is organized by the Department of Mechanical Engineering, Sri Manukala Engineering College. It's my pleasure and privilege to introduce our speaker, Dr.I.A.Palani, Associate Professor, the Department of Mechanical Engineering and Dean, Research and Development, IIT Indore. Welcome you, sir.
Thank you.
He obtained his doctorate from Indian Institute of Technology, Madras. He worked as a postdoctoral research scientist in Graduate School of Information Science and Electrical Engineering, Kyushu University, Japan. He is an instrument for developed mechatronics and instrumentation lab at IIT Indore. His area of expertise include laser-assisted surface processing, micro machining, smart materials, and shape memory alloys. He has published more than 200 international journal publications and having 972 citation index. He also filed 6 Indian patents. He is an executive project for different funding agencies such as DST, SERB, DAT, JSPS, DRDO, MHRD, having a worth of 6 crores. He has closely worked with industries such as Volvo, John Deere, WAPCO as a technical consultant. He has a strong research collaboration with the University of IFW, Dresden University, Germany, Kyushu University, Japan, and Jeju University, South Korea, St. Petersburg State University, Russia, and Purdue University of USA. He is a life member in Indian Laser Association, RRCAT Indore, and Smart Materials and Structure, ISC Bangalore. He has received Alumni Award for the year of 2015 under Research and Innovation Stream. He is a recipient of USH University Friendship Scholarship and AICT National Doctoral Fellowship. So it is our gratitude for his presence in the ATAL FDP program. Now I request Dr. I.A.Palani to take the second session.
So thank you very much for providing me this opportunity on discussing about this design thinking, process of design thinking. The topic which I am going to discuss today is related to biomimicking. So biomimicking, when we hear about this term biomimicking, most of you might be aware about it, that taking nature into confidence is the concept of biomimicking. That is basically, if you take nature, so nature used to teach us in many aspects. Okay, so when we try to take those impacts and when we try to put it up in an engineering or in our day-to-day problems or in our day-to-day where we require technical solutions. So in those things, these biomimicking capability will help us to give a detailed understanding not only about the nature, but also it gives a detailed understanding about the scientific facts and its aspects. Okay, so as far as this biomimicry is concerned, so before going into this is just to give you an overview about our institute. So our institute almost 11 years old institute, and Indore, most of you might be aware about Indore. So it's famous for its very good cricket stadium. And this is about my group. So we work on pneumatic system designs, lasers, and automechatronic systems. So there is a specific area which we call it as smart materials. So we work in the area of smart materials, so which I will be discussing in this forum. So basically, in this forum, I will also be explaining about one of the quite interesting, or I would say an intelligent actuator, which we call it as smart material based actuator, or we call it as shape memory alloys. So these shape memory alloys are a very good catering unit for biomimicking, so which we will be discussing. Okay, so as far as in this thing is concerned, so this image will give you a better clarity, like how we are interlinking the biomimicking capability for our own application. Like for example, so people used to say human body is a very good perfect engineering model. So if you take any kind of complexity, so you can find a solution in a human body. Like one good example I would say is your ball and socket joint. So your ball and socket joint arrangement is a very good system which gives you a very good flexibility for linking as well as picking up. Second thing which I would like to say is about your sensory organ and your strong component, where it's nothing but your skull in which your brain is being stored. So it is hard enough in such a way that it can take care of. So like that, this is with respect to human being. Like for our conventional applications, for our practical applications, so you may need to take some kind of geometries or some kind of operations related to which has a flexibility similar to biomimicking. Like for example, if I want to design a pick and place arm in a robotic system. So in a pick and place arm in a robotic system, normally we take up this motor as an actuator. So this motor, will give you a linear motion, or sometimes it can give you a circular motion where your motors are well adapted for applications. Okay. So, but if you try to look into the overall complexities with respect to static characteristics or with respect to dynamic characteristics, or obviously it has its own limitations with respect to reach, etc. So that is being well taken care with respect to a smart material based actuators or a smart material based systems, where the smart material based systems are well integrated for picking up the system. So like in the case of robotics, biomimicking has taken up a very good shape because of the capability of an actuator which you have used, and because of the complexities which you are employed in your overall systems. In fact, I will be showing you some of the videos where we have used biomimicking concept for handling some of the animals or some of the kind of systems. Okay. So as far as in this case is concerned, so now apart from the robotic, so there are, if you try to look into my biomimicking environment, so in the case of biomimicking, your surface property as well as your overall characteristics is going to play a major role. So your surface property or your when we try to consider our surface property or our overall characteristics, so it is going to cater my biomimicking capability. So that is one interesting aspect with respect to the with respect to the different functionalities. So one good example in which I have shown over here, where you could see that there is a wide varieties of butterflies which are available. So if you try to look into the overall structure of this butterfly, so this butterfly has different textured patterns in it. In the meantime, it gives you a different color. So this, if you closely observe, how does these colors come? So these colors basically come from the amount of light which is emitted from the sun. So this amount of light, either it has a wide spectrum ranging from green color or any other color. Basically, it basically depends upon the optical property of the surface or the making the tailor-made optical property of the surface, which is going to take care or which is going to govern my entire structural unit. Okay. In addition to this, basically, if I try to talk about the optical property, obviously I need to closely look into the features. What kind of features are being generated on the surface? So as far as features is concerned, so there are wide variety of micro or nano features which are being generated on it. So these wide variety of micro or nano features are being encapsulated in such a way that these nano features has a capability for entrapment. So that these capability are well managed in such a way that so it has a capability to tune your optical property as well as your surface characteristics. In fact, when we talk about this biomimicking capability, so the first one which comes to mind is a lotus flower. So basically, in the case of a lotus flower, we see there is a hydrophobic nature which is available. So which basically helps so that the water doesn't fall. So if you closely observe, what is the reason behind that is you have a fine amount of micro patterns or nano patterns which are available. So this micro patterns or nano patterns will help you to make the shape of the system. So that is what we are trying to look at. So as far as in this micro or nano pattern is concerned, so ideally these micro or nano features which are being generated has its own advantage or has its own impact in taking care of the optical property. In fact, this is one good example which I would like to say. So this so this features which has a capability to since it has a capability to manipulate your optical system, so this can be directly employed in a solar cell application. So that in a solar cell application, one major important aspect which we need to work upon is to improve the efficiency of the solar cell. So obviously, to improve the efficiency of the solar cell, what we normally used to do is we create a proper features in it. So when we create a proper feature in it, so obviously it will lead to a higher amount of entrapment. So when it leads to a higher amount of entrapment, it will end up in improving the efficiency of the solar cell. So this is one aspect with respect to the entrapment. Second one, what we are talking about is something related to this particular pattern, where this is an arrangement most of human body has a skin and over which it has a hair kind of structure. So the main function of the hair is to prevent the delicate organs, as well as it also helps us to protect it from the weather environment. Okay, so like if you have a feather kind of arrangement, so these feathers are being fed in a particular direction, so that those feathers are well encapsulated, and it has a pore style kinds of structures which are available in it, and these pores will cater the temperature control. Either you want to have a temperature gradient in your profile, or you want to have, or you want to manipulate your temperature conditions, or you want to protect the system. So you can just create the structure similar to the feather. In fact, this is a very good example where they have taken different types of feathers. Like one is a fur from a bear and a feather from a pigeon, etc. And they have investigated the characteristics inside it in detail through SEM micrograph, and those characteristics were well addressed using in a metallic surface, and these metallic surfaces are being well colored. So this is one example where we have where things are being employed and it is being used for a particular functional application. The next one, if I try to talk about, is something related to correlating your mass or correlating your weight, correlating your geometry with respect to some of the applications. Like one, if you see, so with respect to your body mass, so the nature has its own beauty where it tries to give a different body mass. Based on the body mass, your leg design or your features designs are being well designed. Okay, so based on that, you can select a particular features, and those features can be employed within the system. So one might be a beetle type, or another one might be a fly type. So it might be a spider. So over the spider, you have a patterns which is being placed over here. So these patterns are made to sit on the surface, and these surfaces are well arranged in such a way that you can have a mobile system. So now how you try to fix it up, or how you try to move it in a particular pattern, is going to play a major. Okay, so second thing is, so in this pattern, if you try to see, so I have an animal kind of structure. So in these animals, you are trying to create a features, and these features are going to govern the wear rate or the wear and tear of the system. Like this is one example where they have taken a blue whale arrangement. So in this blue whale, basically the hydrodynamic behavior or the surface over the hydrodynamic behavior is going to have a control over the movement of the system, or going to have the control over the wear and tear. So here on the hydrodynamic behavior, where you have a whale kind of structure which is available. So in these whale kind of structures, when the water is splashing on it, so obviously the wear and tear on the surface is being taken care using a. So the same concept is being employed in tires, so that you have a hydrodynamic force which is being exerting on it. So almost the similar whale kind of structures are being encapsulated in the tires, so that you can have improved wear and tear of this. So these are some of the examples where where biomimicking based capabilities are being employed. But in all these systems, if you see, so based on your application, you are trying to select the parameters. Either it might be an optical parameter, or either it might be a thermal parameter, or either it might be a mechanical components or a mechanical properties are well selected, and then it is being well incorporated in such a way that it almost gives the same functionality similar to your bio capability. Like one more aspect which I would like to say is, nowadays such kind of textures are being incorporated even on a cutting tool or even on a bearing system. So in the case of cutting tool, so you have some kind of patterns which are being generated, so that these patterns which are being generated are well taken care in such a way that it can reduce the overall effect, or it can reduce the wear and tear of the system. And in the case of bearing, so you try to create some kind of texture patterns which are available. So these texture patterns are well managed in such a way that you can have an improved efficiency. So these are some of the concepts which are available, and these concepts are well employed for different applications. Okay. So now with this as an idea, so in today's lecture we will be discussing about the actuators, basically a smart actuators, how a smart actuators has been used for a biomimicking robot. So basically, here I would like to address some of the case studies or some of the work which we have done in our laboratory related to biomimicking, where we have developed our own smart material based actuator for different applications. So if I try to look into the overall characteristics of smart material based actuator, so this is the family of smart material based actuator. So in this family of smart material based actuator is concerned, so you have the shape memory alloy which is available. So this shape memory alloy is going to play a major role, because one good part with the shape memory alloy, it is responsive to. So apart from that, you might have heard about piezoelectric. So the interesting part with these smart material is it can be used as an actuator, or it can be used as a sensor. So it has a dual purpose, so that you can efficiently use it for different applications. Okay. So here I would like to show a small animation which basically explains how a shape memory alloy works. So this is a small lotus leaf which has been manufactured using a shape memory alloy. I think some issues there. So hope you can see a video over here. So you could see a lotus leaf. So this lotus leaf is made out of a metal petal. So I am supplying certain amount of heat to it. and when you try to cut off the heat, it comes back. So basically, so this is a kind of actuator where you can just make tailor-made structures out of it, and these tailor-made structures has a capability in such a way that you can make any kind of component, or you can mimic the nature so easily. So that is a major advantage on going on such kind of systems. So if I come back to the system, so or if I come back to these kind of shape memory alloy based structures, or if I try to look into it, so these shape memory alloys are called as nickel titanium and nitinol. So this nitinol is nothing but nickel titanium naval ordnance lab, since it was developed in a naval ordnance lab. So it has its own standard name. So these standard names. Okay, try playing the video in VLC. Okay, so I think I will play the video at the last. Okay, so in this case, so these shape memory alloys are the combination of nickel titanium, and it has its own applications towards different functional aspects. So if I try to look into them, so any material when we try to design, so any concept or any functionality when we try to talk about, so obviously the material design is going to play a major role, because at the end of the day you are trying to get the final output. Based on your final output, you are trying to map your material property, or you are trying to tune your material property. So as far as in this tunability of your material property is concerned, so this material is getting heated. This material is being well designed based on my requirement. So for that, I need to understand the physics behind these materials. So basically, if I try to probe into it, how these material work. So initially, like it is almost we are taking up the phase diagram of the material. So for example, initially the material is in a solid phase. I'm just heating the solid. It is getting transformed into heat liquid. When I'm further heating this liquid, it is coming up into a gas phase. So if I try to closely observe, so what is happening in this? So you have a austenite phase, you have a martensite phase, and you have a deformed austenite. So you are just flipping it between the austenite and the deformed austenite phase. That is, so you are just you can just take a spring, you are just deforming the spring. So initially the spring is in the martensite phase, you are just applying a heat to it, then it comes back to the austenite phase, and then it's move on. Okay, so this is one a real demonstration which you have done in our laboratory, where you have a spring. So in this spring, a load is getting connected. So when you try to supply a heat, it is being pulled, and when you try to cut off the heat, it comes back. So basically, initially the spring is in a martensite phase. You are going for a deforming the martensite. Then it is on a deformed martensite. Then it comes back to an austenite phase, and then it comes back to a martensite. So like here, temperature is going to play a major role for me to manipulate or to get this displacement. So either in a martensite or in the form of an austenite phase. So you have an electrical actuation which is available. So through this electrical actuation, electrical pulse is being applied and it is moved back. Similarly, in the case of hot water actuation, so in the case of hot water, you have a hot water bowl. So we are just heating it, and we are just deforming these springs in this particular direction. I'm just putting the spring in it, and immediately it comes back to its original shape. So this is an interesting aspect with the shape memory alloys, and this is the overall mechanism which is available. Now, to get the required shape, so I need to train these shape memory alloys. For training these shape memory alloys, what should I need to do is, so I need to make a fixture. So in these fixtures, so I'm just putting up an SMA wire in it. So these SMA wires are well trained, and then it is placed in a hot water, and then when you try to heat it, it gets programmed, it comes back to its shape. So there are different types of materials which exhibits this shape memory alloy property. So like if I try to look into this bifurcation, so the nickel titanium based materials are a certain amount of shape memory alloy materials which has a capability of actuating in the range of 80 to 130 degrees Celsius. Whereas in the case of copper based shape memory alloy structures, so these has a capability in the range of 200 to 350 degrees Celsius. So these are some of the some of the aspects which are available, and these are being incorporated for varying the with respect to your different functional aspects. Okay, now let us go into some of the work where these shape memory alloys are employed for biomimicking applications. So this is one good literature which I would like to talk about, where they have tried to incorporate a kind of a jellyfish kind of arrangement. So in these jellyfish kind of arrangement, so shape memory alloys are being incorporated in the form of a straw. So these shape memory alloys are well trained in such a way that the actuation is taken care, it is being embedded into the composite, so that actuation is taken care and it moves in any particular domain. So basically, so based on that, you can have a back and forth or the movement in this particular direction. So either you can go for a biomimicking, what I would say, a jellyfish kind of arrangement, or one option is you can go for an inchworm kind of arrangement. So in this inchworm, the shape memory alloy is being integrated into it, and the inchworm is made to move. The third one, what we are going to talk about, is something related to meshworm. So in this meshworm, so we are trying to integrate a shape memory alloy inside. So these shape memory alloy are being heated alternatively, or heated or closed alternatively, so that you can get almost a kind of a snail kind of arrangement, or in some cases you can have a earthworm kind of motions which can be elaborated in this. In fact, this is a very good thing which shows you how. Okay, so luckily this is working. So here you could see a kind of arrangement over here, where a jellyfish kind of, an octopus kind of arrangement is available. So in this octopus, a shape memory alloy integrated composite structures is being enabled, and these shape memory alloy integrated composite structures are capable enough in such a way that for providing a crawling motion or a moving motion into the system. So you can almost, so these actuators are going to cater my capability for the movement of the system. So in fact, there is a full video which is available, which I will be showing at the end of my presentation. So the with respect to the biomimicking capability, so we would like to present some of the designs which we have developed in our laboratory in the form of case studies. So the first design which I would like to talk about is a kind of an inchworm mechanism which we have prepared. This inchworm mechanism is something called as a caterpillar kind of mechanism. So in the case of caterpillar kind of mechanism, so we want to mimic a caterpillar movement. So for that, how we are trying to program our actuator and how we are initiating a movement of the system. So that is what we are going to work with. So for that, first we need to understand the motion of the caterpillar. Like see, before designing any robotic system, obviously first we need to understand how the system, how the actual nature works on. So based on that, so we have discretized the mechanism into two. One is a peristaltic crawling, and another one is a two-anchor crawling. So in the peristaltic crawling is concerned, so there is going to be an alternative opening and closing. So alternative elongation and contraction. So with respect to an alternative elongation and contraction, the forward and the return movement is taken. In the case of a two-anchor crawling, so this is almost in a similar fashion, where there is going to be a movement, and this movement is going to fix up in a particular. Okay. So as far as in this case is concerned, so you have a spring which is available. So these springs are well placed in the system. So what we thought is, for this we will use a SMA spring. So first thing is, we need to analyze the capability of it. Basically, we need to check whether these springs which are employed has a capability to go for a peristaltic or a two motion crawling system. So for that, what we made is, so these springs are well attached to these caterpillar kind of arrangement. So the opening and closing of this caterpillar arrangement are well maintained, and then you have a motion which is available over here. So what we did is, we went for a complete modeling of the spring. So obviously, with respect to a modeling of the spring is concerned, so we are trying to study the heating and the cooling behavior of it. So with respect to the heating and the cooling behavior, we are trying to look into the actuation characteristics of it, and we are trying to look into the thermal images in detail. So this is the overall thermal images, and this is the heating and the cooling characteristics of the detonant atom SMS. So you have a meshworm kind of arrangement. So in this, so for creating the overall body of this meshworm, so what we took is, we took a small PET material, like in most of your computers, for wrapping up your wires, you normally use a graded structure. Like I can just show you the graded structure. The graded structure will be something like this. So it's a kind of mesh kind of structure which is available, which is made out of clay. So since we want to program it based on our requirement, so what we made is, we had a solid matter. So over the solid matter, we just place that mesh kind of structure in the form of a saw. We kept it on a hot furnace, and then we heated the material and we went for an air cooling. And then with respect to the air cooling, there was a kind of soft structure which was getting generated. So these structures, so soft structures are well being what I would say is wrapped with a shape memory alloy spring, so to get the required displacement. So what we made is, this is a SMA phase transformation which is available, and this is initially in a twinned martin cell, and it is in a D10 martin cell, where we are just using a PET loading, and with respect to displacement, we are trying to study the characteristics. So what we did is, we took a raw bed, then we annealed this bed for based on our requirement. So this is a bed which is being integrated with a spring. So we went for a different configuration for getting the different locomotive movement. So since we have already are exposed to this peristaltic as well as a crawling movement, so one kind of arrangement is something like this, where the braided tube is well peened with SMA spring, and another one in which the SMA spring is being well wounded off, so that you get an actuation coming out. And this is your Keton polyamide weight which is available, and you get an appropriate actuation for the movement. So we made a complete closed loop system in our unit. So this is an open loop unit. So as the next level, we have went for a closed loop system. So in this open loop system, what we made is, so we had a software and we have a laser displacement sensor kind of arrangement. And here you have a programmable power supply, and you have a data acquisition system which is available. So in the case of a data acquisition system, so from the LDA sensor, so you have a data acquisition system which is there, and where you are trying to tap the signal coming out of it. The entire controller is taken care using an Arduino software, because the overall structure what we are working upon is complex enough, so that we should take a miniature size controller, so that it can be well embedded within the system, so that it becomes an autonomous. And it is being well fitted up with a programmable power supply, and the inch-worm inspired software robotic systems are being employed. Okay, so initially what we thought is, so since we are using a spring, so we want to study the overall characteristics of this actuator what we are using. So in fact, we went for, we designed our own test bed setup. So in this test bed setup, we had a spring, and we had a weight which is being placed over here, and we have a LDA sensor, and you have a DAC unit which is available. So there was opening and closing, or I would say the actuation which was moving upon. So this actuation helped us to move the weight in different orientation, so that this helped us to study the overall displacement. So with respect to the overall displacement, we could study the characteristics, or I would say we could able to predict the life cycle behavior of the system. So for this, since we are using a current as an actuation medium, so we are just employing the current into the system, and using this, we were trying to study the overall life cycle behavior in it. So this was the structure, how we have developed. So in this structure, our main concern is the bending angle. So with respect to the bending angle, with respect to time, we were just trying to study in detail, and we were also trying to study the recovery characteristics. So with respect to the recovery, we were trying to study the overall behavior, what is happening within the system. And here we are trying to integrate the flux sensor inside it, so that this flux sensor will give me the measurement about the bend angle and about the flexibility of it. So this is the measurement kind of arrangement, so which we have made. And in order to give a locomotion to the system, so we went for different mechanisms. So one is with respect to the upward mechanism which is available. Another one is with the left bending which is available. So another one is with the right bending which is available. So by an alternative actuation, so we can get a flipping arrangement which is coming into the picture. And these flipping arrangement characteristics we are studied in detail. So basically, for performance analysis, we studied the effect of bend angle and with respect to time t. So because here in this concern, the response time is going to play a major. So with respect to my response time, so I'm going to study my bend angle. Basically, an idea what we have in mind for such kind of systems are like you take a trip. So like most of you might have seen when a snake is climbing a coconut. So when a snake tries to climb a coconut tree, normally what will happen is it will have an alternate expansion and contraction. So when there is an alternate expansion and contraction which is available, so it is going to end up in such a way that it will try to climb the tree in that particular. So it will try to grip towards the tree, and there will be an alternate expansion and contraction. So this alternate expansion and contraction will help the animal to move forward and climb the tree. Or the other option would be if you have a reverse expansion and contraction. So this will help to move backward. So this is one arrangement which you can think of. So as far as in this case is concerned, so you have a mesh one kind of arrangement. So this mesh one kind of arrangements are being well programmed in such a way that you have a spring which is being placed over here, so that the alternative opening and closing of the spring will help us for the move. Okay, so this is how we were trying to study the performance evaluation. So in this performance evaluation, so we were just trying to study the bend angle and with respect to time. So with respect to time t and with respect to the bend angle, so we were trying to predict the peristaltic crawling in detail, or I would say that we were trying to observe the peristaltic crawling and how it is being employed. In fact, this is a small animation which shows, this is a small video which shows how our system was working upon. So this is the braided structure, and here you have a spring which is available. So we are trying to give an electrical pulse to it. So with respect to an electrical pulse, it is giving a deflection. So this is how is the flexibility of the system. So inside this system, we have almost incorporated our onboard controller. So this is one kind of peristaltic locomotion which we have employed for maneuvering in a single stair arrangement, and this is a bending action to get a two anchor locomotion. So as far as this two anchor locomotion is concerned, so it gives a movement in a stroke so that we can work. Okay, so as far as in this peristaltic locomotion or maneuvering is concerned, so based on your functionality, so you are trying to create, you are trying to give your pulse signal, and with respect to your pulse signal, so you are trying to have a control over your locomotion or towards your dynamics. So this is how your system is being designed. Okay, but here in this case, like we also want to employ this in some of the nuclear reactors, since it is quite successful that it could deliver a peristaltic and a crawling motion similar to a inchworm, similar to a earthworm, or similar to a snake. So what we thought is, so if we for example, I have a nuclear reactor or I have a chamber. So inside this chamber, so these systems has to move upon, where I need to go for a non-contact based actuation, because if I try to put a tether of electrical signal, it will be very difficult for me to follow. So what we thought is, why can't we use a laser? So like, since this SMA requires a heat, so why can't we use a non-contact laser to heat the material so that there will be an actuation which is coming. So that is what an idea what we thought. So with this as an idea, so we took the actuator. So this actuator was scanned through the laser, and this is the weight which is being employed into it. So we try to scan the laser over the spring, and we were trying to study the displacement. So in fact, we studied the displacement with respect to number of passes and the power. And by changing the power and with respect to number of passes, we were trying to study the overall characteristics of it. And this is the displacement, and this is with respect to power. And with respect to the variation in displacement, we were trying to look into the power capability of it. And then in addition to that, there are number of passes which are available. So the influence of number of passes with respect to the power capability and the displacement were also studied. In fact, this is the setup what we use. So this is the soft mesh type of structures which we have used for our system. And this is a laser which is being employed in. So this laser in the soft mesh structure, so we have incorporated the shape memory alloy structure in it. So in these shape memory alloy structures, so the mirror were made to move upon, and when these mirror were made to move upon, there was a deflection which was coming. Okay, so this is how, if you see, this is a video which was taken. So this is the mesh worm kind of arrangement, and this is your shape memory alloy, and this is a non-contact laser. So the non-contact laser is made to irradiate on the surface of the spring. So when it is made to irradiate on the surface of the spring, so there is going to be a deflection which is coming up, and that deflection is well studied. So this is these are some of the summaries which with respect to this particular thing. So where we could achieve a better angle. So basically we tried to study the thermomechanical behavior of these actuators. So these thermomechanical behaviors were studied with respect to the different load conditions. We also had we also studied with respect to the bending angle capability, with respect to the bending angle capability, how the system was working upon, and with respect to the laser actuation, how the movement was being controlled. So this is our first case study where we have developed a small mushroom kind of. So the second case study which I would like to discuss about is we have developed a small soft robotic fish using an SMA actuated spring. It's an underwater robotic system. So like as far as sea fish is concerned, wide varieties of sea fishes are available. So the idea or motivation behind this system is, so this fish what we have developed is of a rare species. So so this is basically meant for almost diverting a swarm or crowd of fish which is available in the sea to move it in a particular direction. So in fact, what we made is, so we had we almost had a 3D print kind of structures. So in this 3D print kind of structures, we have fixed up the SMS spring, and we had a head which is available, and we had a cloudler fin which is available. So this cloudler fin, so when you try to actuate it, this cloudler fin will help to maintain the buoyancy and for the appropriate movement. And on the head, you have a power socket which is available, and the power is being appropriately fed into the SMS spring. And the opening of the actuation of this SMS spring helps us to move it in a forward shape. Okay, so this is one arrangement what we have. So as far as in this SMS spring is concerned, so the movement of the stroke is being well taken care using this tool. So as far as, so in this case, you have a rib kind of arrangement, you have a SMS springs which is available, and we have to design the system based on the buoyancy. So what we made is, so initially before putting up in the form of a complete experimental structure, so what we thought is we will build a complete model. So this model was prepared in such a way that, so we almost had a 3D printed bone kind of structure. So in these 3D printed bone kind of structures, we just incorporated the SMS spring inside it, and we had a cloud kind of arrangement, and there was a head, there was a fish head which was available, over which our power supply was being incorporated. So this movement has to be well controlled in such a way that you need to take care of the buoyancy. So what we did is, we took the actual fish, we took the video of the actual fish. So we almost captured the each and every nodes and nuances of the motion from each and every nodes, and that we have programmed it in our controller. And based on that, we designed our skeletal structure of the fish. So in the skeletal structure of the fish, so the entire skeletal structure were made using a 3D printed mold, and the bone region was being, I would say, the nerve region is being well replaced with the springs. So that we were more interested to know how much is the frequency required for an appropriate mode. So by giving an alternative current to it, so you are just trying to induce the frequency, or you are trying to induce an activation to it, so that the forward stroke is well taken care of. So when we try to plot the distance, so our major concern is, so we want to optimize the frequency for our application. So for that, what we made is, we almost took a displacement versus time graph. So with respect to our displacement versus time graph, we try to change the frequency. One is with 0.5 hertz and one is with 0.1 hertz. So with 0.5 hertz, how the frequency was changing, and with respect to 0.1 hertz, how the frequency was changing. So we had a kinematic system. So in fact, we want to study the overall kinematics of the system. So in the system, what we made is, so we made a different geometry. That is, I would say that we made a different reference. From that, we analyzed the TS parameter. So basically, we did a complete dynamic calculations to give or to study how much is the maximum displacement which can be achieved. And from that maximum displacement, you can say how much is your node which is being incorporated into it, and how is your robotic fish head which is being employed. And here is where exactly our SMA spring was being taken. So this was a complete robotic design which we have incorporated in this, so that we know what kind of output we require. So that output plots, or I would say that output references were incorporated in each and every joint, and then appropriate control strategies were developed to give a programming to the system for the move. So this is a complete theoretical analysis which we did. So basically, we discretized the fish into 3 regions. So one is your head part, another one is your fish body part, and third is your flexibility part. So this entire structure was fabricated in our laboratory. So this structure was 3D printed. This structure was also 3D printed. So this will take care of the buoyancy, because this fish has a habit of moving downwards by keeping his head. So if it wants to dive, basically it keeps his head downwards to move in the direction. So accordingly, so based on the head motion, so obviously you need to design your flexible fin. So what we made is, so we had an arrangement over here where we had a head, we had a body link, and we have a cloud fin which is available. And in this head, you had a cloud fin with an angle, and this is your length. And based on your movement, we could have a control over it. So this is the overall structure which is being incorporated over here. So in this overall structure, you have a tail, you have a body, and you have a head which is available, and you have a SMA spring which is being placed. So these SMA springs are actuated in appropriate fashion, and this is your 3D printed fish body, and this is your flexible fin which is available, and this is your 3D printed fish. So inside this 3D printed fish head, you have a battery arrangement which is available, so that this battery will try to give the pulse for the depth. Whereas once it reaches a particular domain, so automatically we have made some kind of piezoelectric structures which are being incorporated over here because of the ocean current. So these will try to capture the energy, and it will be helpful for me for the floating movement or for the forward stroke movement, which is being well taken care using this system. So this is our overall control circuit what we made. So in fact, this is a bare minimum control circuit which we have employed for our system. So there was an Arduino board which was available, and we had a complete set of relay circuits which are being kept over here. And we have arranged a shared memory alloy structure in a different fashion. So wherever we require, so each and every shared memory alloy was restricted to the displacement. Like for example, the shared memory alloy which is being integrated near to the tail doesn't require a complete spectrum. Okay. So in those conditions, sorry, in the shared memory alloy structure which is kept near to the tail, so has to displace on a higher order than the shared memory alloy structure which is available near to the tail. So with that as an idea, so obviously, so we need to feed our relay in such a way that, so whatever program we have run in our Arduino, so that Arduino is well programmed, and the signal is being fed into the relay, and those relay signals are being fed into the SMS structure, so that you are trying to apply a constraint to it for the movement of the fish body based system. And in fact, this is the performance evaluation which is we did for the system. So we had a tank. So inside this tank, we are just putting up the unit, and we are trying to actuate it. And here you have a LDS sensor. So this LDS sensor was moving, and this LDS sensor performance was being investigated over here, and the displacement versus time characteristics were investigated. So in fact, we want to have a complete consistency in our displacement versus time characteristics. So with respect to this consistency, we were trying to study the detailed behavior. Okay, so this is how we have studied our performance evaluation. In fact, we took the central axis. So along the central axis, we had 3D printed structures, and we just kept our shape memory aligned in this direction. So we know what is the limit of the tail which needs to move from right to left. So based on the limit of the tail, so we are trying to apply a programming signal to it. So by just applying a programming signal to it, so obviously you are trying to have a control over the movement while. Okay, so this is how we have done our performance evaluation on a real time. So in fact, this is on a lab scale. So we took a bucket of water and we created our own waviness on it. So since we have optimized our frequency, so that by giving an appropriate frequency, so you can have you can almost control your movement on it. So in fact, we tested with different frequencies. So this is a complete onboard controller. So this was done before PCB. So after it has been formulated in the form of PCB, so the entire system was coming inside the head portion, so that the buoyancy was well taken care. And we also studied the force produced by these SMA mechanism in detail, because this force will be helpful for me to study the dynamics of this. Okay, so because you are talking about something related to underwater current and underwater buoyancy. So in the case of underwater buoyancy, so how much is the depth what we have achieved, and with respect to the depth, how much is the system which is being moving on. Okay, so this is the relay circuit which we have made, and this is the kind of arrangement which we have tested, and this is a small test bed we have developed in our lab. So in this test bed, so there was a kind of a transparent tank which was available. So this inside this transparent tank, even though we had an onboard controller on the top, so this transparent tank has a capability to simulate a wave. So what we made is we made a pneumatic system kind of arrangement. So this pneumatic system was creating some kind of signals, whatever sinusoidal signals. So these sinusoidal signals are being fed into these fish region, and you are trying to tap this. And this is how our system was working upon. So in fact, at the end, I'll be showing you a video where you can just see a clarity how this fish was swimming and was taking care of the motion. So this is with respect to an onboard controller. So we created some kind of undulations, and we were trying to look into the configuration. In fact, we went for 2-3 configurations. So with respect to these 2-3 configurations, so we were trying to study the characteristics of the float or the characteristics of the buoyancy. So this is how we have done our performance evaluation, because here 2 major design criteria will come. So one is the thermal characteristics to take care of my actuation in the shape member alloy. Another one is the buoyancy characteristics, which is coming from the fluid. So in fact, we went for a complete theoretical and experimental analysis, and we are successful to biomimic a complete robotic fish in this platform. So and this testbed, with what we have developed, has a capability to change the frequency at different patterns, and from these frequencies we could able to study how the system is working. Okay. So the next case study which I would like to talk about is, so we have developed a small robotic gripper. Okay, so this gripper, we in the robotic terminology, we normally call it as end effector. So this end effector has a capability in such a way that this end effector can move back and forth, and then so from this end effector, you can just hold any kind of component or any kind of systems working. So here, like for this end effector, since we want to have a delicate end effectors to hold some kind of delicate component, so what we made is, so we have, since we have a very good actuator with us, so we want to integrate these actuators in the kind of a composite structure. So we had a transparent composite structure. So inside these composite structures, so we have incorporated a shape memory alloy wire in it. So these shape memory alloy wires are well strained, and it is being fitted up with a composite structure, so that when you try to actuate it, there is a kind of flipping motion which is available, or some kind of arrangement which is coming upon. And with respect to an alternative actuation, so you can just have a displacement coming over. In fact, so this is the kind of arrangement. So what we have made. So in this arrangement, so what we have done is we have taken a wire and we have strained this wire, and then inside this, these strained wires are well packed inside a transparent composite layer. So these composite layer are well actuated, so that you can see the deflection coming. So this is the temperature, and this is the surface temperature which we are trying to come upon. So first, initially we simulated, because here in most of this gripper, so the power consumption is going to play a major. So I need to be well versed about my power consumption before I am trying to put up my system in the actual environment. So what I did is, so we did a complete theoretical simulation with respect to the heat transfer characteristics to optimize my power consumption. Then these are some of the concepts which are being employed for fabrication. So where I have kind of fixture kind of arrangement. So in this fixture kind of arrangement, so we have kept a shape memory alloy wire which is being strained. So over the shape memory alloy, you have we have made a fixture. So over this fixture, we are trying to put up a composite layer. So in these composite layers, so a thin layer of composite material will be on the surface, and then we are adding up a PDMS layer to it. So these PDMS layers are well mixed, and then with respect to an appropriate actuation, so you are trying to look into the capability. So this is the CAD model which is being employed, and this is a 3D printed model. So inside this 3D printed model, you are trying to fixing up the system. So in these fixing up the systems, so you are trying to push up the wire inside, and these PDMS structures are well being maintained, and the actuation is being done. So in fact, this is how the structure looks like. So in this structure, so this is almost kind of a small transparent layer which is available, and which is slightly flexible, and it has a capability, and it is delicate to hold any kind of component. So we have developed a setup. So basically, whenever we are designing this actuator, normally we will run this actuator till it fails, because the reason is here since we are directly putting up in a system which is going to cater the human needs. So what we thought is, so instead we run the actuator till the end to study the reliability as well as to study the failure of it. So for that we have developed this setup. So this setup has a power source, which is a programmable power source. So the power source, the programmable power source is fed into this PDMS layer, and this is your control system unit which is available. So through this control system, a programming pulse is being employed, and these programming pulse is being employed in such a way that there is going to be a back and forth movement which is going to come upon, and you have an LDS which is being well connected to a data admission system, and this is your PC. So from your PC, you are trying to tap your signal, and you are trying to look into the overall characteristics. So this is how we have studied the overall characteristics. In fact, the major defect which may happen is sometime a delamination. Sometimes the shape memory alloy may lose its property. So what we have done is, so basically we have a performance evaluation. So we have displacement characteristics which is available, and with respect to these displacement characteristics, we are trying to study the behavior. So this is the permanent deformation behavior which was fed after almost 1 lakh cycle at higher current. So how much is the defect which is being coming upon, and we were also looking into the overall performance. So in fact, this is the life cycle of the overall performance of this soft actuator. So this is up to 2000 cycles. So in fact, with a shorter frequency. So even we have gone up to 1 lakh where there was no distortion, but after a 2.5 lakh cycle, there was a slight reduction, or there was a slight reduction in the performance which was observed, which is going to be one of the measures. Okay, so this is the gripper what we designed. Obviously, this is a kind of a crude gripper, so which we were just looking into the application of it. So this is your PDMS structure, and this is an SMA wire which is being employed. So these SMA wire are being well programmed, so that when you try to actuate it, this gripper moves back and forth. In fact, I think I have a small demonstration. So basically, this is a kind of initial training which we have done. So we went to train the shape memory alloy structures with different payload. So this is with 2.5 grams, this is with 3.5 grams, and this is with 7 grams. So we were trying to actuate it. So, and we were trying to quickly press it in this direction to firmly hold the system. Okay, so this is the overall summary about this particular module. So where we could a maximum surface of temperature of 27.6 degrees Celsius has been found through the simulation, and the same has been validated to the thermographic camera. And in fact, the electrical actuation development of these software showed a maximum displacement of 7.5 mm with a 2 amps current. In fact, we went for different pre-training, because if you see in this, so your gripping capability basically depends upon how much you are pre-straining your ball. So the more you the amount of percentage you pre-strain will have a control over the holding of the system. So what we made is, so we had a different pre-strain options. So one is with 5%, another one is 8% pre-strain, which we have applied in it. And these pre-strains are appropriately tension, so that it in such a way that it can hold. Okay, so and in fact we went for a cyclic behavior analysis to show the average displacement, and we also studied in detail. So the maximum we could achieve was around 7 grams. So which is mainly meant for holding some kind of delicate silicon wafers over the system. So the next module which I would like to discuss about is something kind of a robotic jellyfish which we have developed. So this was in collaboration with NPOL Kochi. So basically the idea of this system is basically, so we took some of the input from NPOL Kochi to develop this unit. So like this has a onboard camera in it, so that it can go into a deep sea. So when it goes into the deep sea, so it can capture the image, like for example, if some diver is diving into it, so it can capture the image and it can send the signal to the onboard system. So that is what an idea, what we thought of. So this is the soft robotic jellyfish which you have actuated. So we had a polyimide kind of structure. So basically this is a SMA coated polyimide. So in this polyimide, what we made is, so this polyimide is slightly flexible. So in this polyimide, so we were trying to incorporate shape memory alloy wire in it. so that these strained shape memory alloy wires are well packed and it is being fed into the rubber material. And when I try to actuate it, the actuation happens in such a way that it has a control over frequency. And then you have a rubber string which is available, and the rubber string is used for an actuation behavior. In fact, this is the overall construction what we have made. So this rubber string will take care of the negative deflection, and the shape memory alloy will take care of the positive deflection which is available. So this is being well integrated in such a way that you can have oscillating movement, and this oscillating movement will take care of the balance. So in fact, we went for a complete kinematic model. So as in this kinematic model is concerned, so this is a bit complex because this kinematic model is a bit flexible, and you are trying to incorporate shape memory alloy wire in it. So these strained shape memory alloy wires are well packed inside these structures. So by actuating it, you are trying to create a flap, and from this flapping mechanism, you are trying to harvest it. Okay, so and this is kinematic model which we have designed for. So in this kinematic model, so we have made a matrix. So these matrices were appropriately taken in such a way that each and every nodes of displacements were studied in detail, or I would say each and every nodes of displacement were designed in detail to get an appropriate displacement outcome. So basically, this will give me a summary about the alpha angle as well as the theta which is required for it. So we went for a dynamic model. So in fact, we took a Newton-Euler algorithm to define this dynamic model. So and we almost discretized these systems into different links, and these links are well programmed to study how much is the maximum displacement which was coming upon. So this was the simulation for trajectory which we have done in Adams, where what we have done is the different nodes of the systems were taken it up, and then it was simulated so that to see how much is the maximum displacement or the maximum angle which you could achieve. Okay, so this is a fin model simulation using an Adams platform. So where we took one tentacle, and these tentacles were strained at different conditions, and the effect of these tentacles were studied. And most important is the effect of displacement with respect to time, and the effect of velocity with respect to time were also studied in detail. Okay, so this is this is a small biomorph which we have made. So inside this biomorph, we have elastic band kind of arrangement. So this elastic band, we are moving in a particular movement, and these elastic band we are trying to. So we were trying to extract the bending moment out of it. So so from this bending moment, so we could able to study the stiffness of it. So with that you can try to study the actuation behavior. So we want to investigate the resolution of this actuator what we have used. So the resolution what we have used, so we have we have investigated the temperature versus time. So with respect to the temperature versus time, so we were trying to flap it, and these flapping mechanisms were appropriately recorded. So this is with respect to the different electrical pulse. So there was a flapping mechanism which was uptime, and these flapping mechanisms were studied in detail. So this is the temperature versus time graph, and this is the deflection with respect to the modulus of the system what we have employed in our unit as was demonstrated. In fact, each and every tentacle deflection were studied, because based on your movement, obviously your tentacle will get deflect, and that tentacle deflections can give me a better prospect with respect to the different applications. And we also did a small hydrodynamic analysis, since it is going for an underwater application. So this is an hydrodynamic analysis in a ANSYS platform. So what we did is so these are the different tentacles which are being made, and we have since we are planning to incorporate a shape memory alloy structure in it. So the characteristics of the shape memory alloy structures are well modeled, and it is being well fitted into these tentacles. So and the actuation characteristics we have studied in it. So this is the static pressure which is available, and this is the velocity vectors which are available. And we have studied the static pressure distribution and the velocity vector distribution in detail. So the static pressure distribution and the velocity vector distribution we are investigated in detail, and this is the effect with respect to the horizontal orientation. And with respect to an horizontal orientation, we were trying to study the overall contraction and the pressure control, as well as the vortex formation which is being available over here. So this is the complete hydrodynamic studies which we have done. So this is with respect to an expansion and contraction which is available, and this is with respect to a vortex motion which was happening. So this vortex motion helps us to study the overall behavior, and it also gives a clarity in such a way that how much is the motion which is being picked up, and in which direction this motion is being taken. So this is the simulation of the real jellyfish, and these hydrodynamic parameters were incorporated in our system. So basically the environment of the system were being taken care, and the contraction and the expansion characteristics were set. So here also, so we also investigated the thrust force, and we also studied the overall time displacement characteristics with respect to the thrust force to see how the tentacle behaves with respect to the different hydrodynamic behavior. So this was our overall construction. So this is the polyimide structure. So inside these polyimide structures, so we had a shape memory alloy which is being integrated into it. So we are trying to supply heat to it, and this is at rest and this is at actuation. So this is on a rest condition, and when I try to give an electrical pulse to it, so you are trying to move along the actuation. So this is so we were trying to capture the displacement of each and every tentacles using a high-speed camera to see how it is well correlated with respect to the biomimicking capability. So this is almost, it is something like we have simulated the effect of frequency towards the movement of the tentacle. So that is also well justified with respect to this particular movement. So say here what we have done is, so we have done a complete performance evaluation with respect to different frequency, and we were trying to study about the influence of displacement with respect to time. So this is the performance evaluation characteristics, where we are trying to study in detail about the different tentacle bending angle, and these tentacle bending angle investigations were taken up. So this is the overall structure of our system, and here you have a camera, and this is the flux sensor which is being incorporated into it. And these flux sensors, so by giving actuation to it, so the flux sensor will try to tap the signal, and the camera and the electronic control which is available will try to trap the system which is available. So this is how we have gone for a performance evaluation, where there is a load cell is there. So this helped us to investigate the force calculation in this entire system. And this is a tie rod which we have made, and over this tie rod there is a soft robotic jellyfish, and we have simulated the different water current over here, and from that we were trying to study how the force was generated and how the controller has behaved to give an actuation to this particular tentacle for a complete movement. In fact, this is animated video about real-time jellyfish, and this is the jellyfish which we have developed in our laboratory by considering all the parameters. So this is a kind of underwater movement which is available. So it almost has a similar tentacle arrangement, and the tentacle feet were also given in a particular direction for the forward movement. So currently we are just using a tether onboard controller with tether, so that the power is being fed in this particular direction. Okay. So and this is one arrangement over here when it tries to move along a deep sea kind of motion. So this is a real jellyfish which moves along a deep sea. So this is the jellyfish which we have developed in our laboratory by taking up the signal from it. So almost the deep sea environment we have created. So there will be an expansion and contraction of the jellyfish. So this is the expansion and the contraction of the jellyfish for the movement in a forward stroke. So basically, these images were taken with a high-speed camera to see how the movement is moving upon and how the motions are being taken. So almost we were trying to mimic the natural jellyfish, and we were trying to map the speed of the natural jellyfish. So this is images of the high-speed camera of our jellyfish, both in a vertical orientation and in a horizontal orientation, to see how much is disturbed. So this is one system what we have made in such a way that we want to incorporate a power node in. So through this power node, so you can have a control over the buoyancy, and we could see how it is happening. So this is some kind of configuration which we attempted, so that the power node will act as a negative deflection unit, and these negative deflection units are well compensated with respect to the positive deflection from the shared memory lines. So this is a final system which currently it is on the test bed situation, where we have incorporated a flux sensor, and here we have also used a sonar sensor. This is a transparent region where a camera is being fed into it. So using a camera, you can just capture the image, and the systems and the signal is being fed. So this is a camera model, and this is the arrangement what we made, and this is a kind of tentacle. So this is the overall summary of this. So in this summary, what we have made is we have achieved a maximum displacement of around 15.3 mm, and we have just tuned our frequency, because this frequency characteristics is going to play a major role with respect to my application. So we have checked the different characteristics like 0.5 hertz, 2 hertz, etc. And we have also studied the load bearing capacity of it, and with respect to the load bearing capacity, how the jellyfish structures are being incorporated. Okay, so this is a complete PDMS structure. See, the interesting part with this structure is normally when you try to use a motor, so there are some kind of systems which have been developed in similar fashion with the motor, but motor will give a sound which can be easily picked up by the enemy radar. So whereas these kind of systems are silent actuators, so it almost similar to a real time jellyfish. So when a person from the other end he feels that it is a real time jellyfish. So the next one which I would like to talk about is something kind of, we have developed a small aerial robot, which is almost similar kind of a dragonfly kind of. So for this aerial robot, again the major thing which I need to look upon is the actuator which I need to use. So what we made is like for this arrangement, so we are thinking of making up some kind of butterfly kind of configuration. So what we thought is we made a small dragonfly. We took a dragonfly as an example. So in this dragonfly, a dragonfly, if you see, it has a very delicate beam, and it actuates at a very high frequency, around 8 to 10 hertz, even sometimes more than. So we want to develop a shared memory alloy actuator which can almost exert such an amount of frequency. So for that, what we made is we came up with a technology called bimorph. So this bimorph is something like one area is made out of polymer, and the top area is coated with shared memory alloy. So the shared memory alloy is actuated in such a way that, so one way of deflection is taken care using a shared memory alloy, and the reverse deflection is being taken care using a polyamide structure. So this polyamide, so when you try to apply a frequency, so you get a particular frequency coming out of it, and these frequencies are well established. Okay, so this is a polyamide, and this is an SMA thin film which is being coated on. So over this SMA thin film, so you are trying to actuate it, and you are trying to look into the frequency. Okay, so we went for a complete theoretical analysis. So because since it's a thin film, so there is a chance that it may end up in some kind of stressors. And the idea of what we have employed is like like for example, I take a rubber, I just elongate the rubber band and I try to put a thick cellophane tape on. So one way the cellophane will try to restrict the release of the rubber. Okay, but even when it gets released, so either of the composite structure is going to contribute for some kind of function. So the same thing is happening over here. So what we made is we made an arrangement in such a way that you are trying to apply a strain to your polyamide, and then you are going to go for a deposition. So this deposition is going to get deposited in such a way that, so one way actuation is taken care by the shared memory alloy, and the return actuation is going to take care with respect to the polyamide structure which is going to come. So this is the SMA bimorph. So over this SMA bimorph, so we have coated the structure, and then we are trying to actuate it so that you get a deflection coming out. Okay, so this is a kind of arrangement what we made in our lab to make a certain amount of bimorph based structures. So in these bimorph based structures, so one important key parameter is the thickness of the polyamide what I am using. So I can go for a 25 micrometer or a 50 micrometer or a 75 micrometer, which is going to govern my frequency characteristics. So that's how I have designed. So here also, so before deploying this actuator in some kind of functional work, so obviously I need to go for some kind of arrangement where I need to employ a complete unit where I have a programmable power supply and I have an LDS sensor which is being played. So this LDS sensor is being fed into this bimorph, and the return stroke is being taken. So the actuation characteristics is moved in such a way that, so the LDS will try to pick up the signal, and from that we are trying to move. So this is a lab view, and so we have made a complete open loop system we have made a complete closed loop system with a LabVIEW program to study the characteristics. This is how we have studied the overall performance of the system, and we were trying to tap the overall reading. So basically, it is something like we are trying to go for an alternate heating and cooling characteristics in detail. Okay, and we went for a complete control strategy to, and we almost fed our set point to get a proper thing. And these are some of the controller tuning which was employed to give a appropriate control strategies. Okay, and we went for a complete set point characteristics to study the control behavior. So this is an arrangement what we made. So this is so along with the aerial robot, we also made some kind of a steward platform kind of arrangement, so that the steward platform, so when you try to actuate it, so it can work as a walking robot, as well as it can be used for diverting them. So this entire system is being well taken care by incorporating a control and incorporating an appropriate strategies. Obviously, this is currently on a development phase, and we are working upon it. This is a kind of arrangement what we are moving on. Okay, so this is almost this idea we took it from a spider. So basically, in the spider has 8 legs, and the top base it has a capability to rotate. So like even when it tries to move, it has a very common fixed form. So that with that idea, we made this steward platform with a leg actuation as well as twisting arrangement, so that it has a capability to move back and forth, and it has a control over the base over which it is being moved. So before the closing into it, so I would like to show you some videos related to the actuation, related to the characteristics. So this is one video about the robotic steward platform. So Thiago sir, could you able to see this video? Thiago sir? Okay. Yeah.
No, sir. You just try to open.
Okay.
You're not getting your video, sir, right now.
1 minute ago. 1 minute ago.
Okay, we will wait, sir.
Could you able to see the video now?
Yes, sir.
So this is a kind of arrangement where it's a kind of octopus kind of arrangement where we have complete shape memory like composite structure which is available. So when you try to actuate it, so you can have a move. So you have a different arms which is being placed. For appropriate movement, you are trying to give a control to the different arms. So the next one which I would like to show is the one which has a. I would like to show a video about my lab and some of the work which we have done with respect to biomimetic applications. Here I need to, for each and everything, I need to share individually. Could you able to see the video?
Yes, sir. We are getting it. Indian Institute of Technology, Indore. Okay, sir.
Okay. So these are some of the facilities which are available. So we have a strong thin film facilities which are available in our lab, either EV, flash operation, etc. So we have a strong characterization facilities, and we have different types of lasers with us. So for different applications, recently we have also got a project with mines for laser mining, etc. And these are different types of 3D printers which are available. In fact, one metal 3D printer we have developed in-house in our laboratory. So that at a very lower cost, like around within 3 lakhs, including the software and including the controller we have developed. So this metal 3D printer is dedicated only for shape memory lights, for making shape memory lights, bulk shape memory lights for different structures. So these are some of the structures which we have fabricated using shape memory lights. So this machine has a capability to print even solid structures of around 30 centimeters. So you can print a sphere also. And now currently we have made an arrangement in such a way that this this unit can have a control over the grain growth. This is a wire rack based additive manufacturing. So this is the shape memory alloy reliability study. So whatever shape memory alloy structures we do, normally we make a reliability study out of it, and we try to look into the failure of it. So the failure characteristics we are trying to we will be working. Still, we don't have a confidence. We won't deploy it in the field. This is one laser actuation setup which we have made for shaping. This is a laser forming unit which we have done it for one of the company for making engine cabinets. So, it's a part of a die-less manufacturing where we use a laser for. So this is a small shape umbrella integrated composite flapper which we have developed for DRDO for a missile application. So it's a kind of a handheld missile which is being maneuvered using this kind of. So this is a SMA heat engine. So which is it's a kind of a perpetual mission where you can harvest the energy from hot water. So this is the bimorph which I was talking about, where we have made a small aerial robot. So this is the jellyfish which we have fabricated in our lab. So I think this video will be pretty clear. So this is a kind of a piezoelectric structure which we have developed in-house in our lab. So these piezoelectric structures are something like it's a lead-free piezoelectric. So there is no it's a biodegradable. So a student is demonstrating some kind of reaction, so that here there is no energy. How much ever he stamps on it, based on that, the amount of energy is getting released, and the reaction is being well. So this is a burglar alarm which we have developed with a piezoelectric. It's a smart burglar alarm. So when people step on it, automatically the burglar alarm will come. So this is a kind of piezoelectric based flag. So this flag, fluttering of the flag is taken care in such a way that, so you are trying to harvest the energy of it. So this is a piezoelectric structure which is used for monitoring the compressor. So we have just pasted the piezoelectric structure. And we are trying to harvest the energy from compressor. In fact, this is used as one of the component for industry 4.0 applications. So with this, I would like to close my lecture. I'll be happy to address any kind of questions. So is there any question in the chat box?
Okay, sir.
Okay, very good. Okay, so I think we will start with
Sir, any other video you want to share? Otherwise,
no, yeah. I think I'm done with. So we can start with the question. I think some questions are there in the chat box, right? Can you please clarify? There is one question from Gurupreet Kaur. Can you please clarify the design thinking process framework for your research in steps or as process? Okay. See, as far as this biomimicking is concerned, normally we take so we have a problem identification. So based on the problem identification, we try to select the solution from the nature. So like in the case of this jellyfish. Okay, so jellyfish, when we try to use it for some kind of defense application, two major things we need to work upon. One is it should escape from the enemy radar. So basically it should have, second thing is with respect to its performance. So obviously we take the design framework from the nature, which has a similar functionality, and we based on that we try to select our parameters, and based on the parameters, obviously for any kind of such kind of systems, actuators and sensors are going to play a major. So the first option would be we try to get the sensor which is commercially available. If not so, then we will opt for a technique where we try to fabricate the sensor for our own requirement. So that is what the idea basically, I would say that is the preliminary idea what we start with. But later in due course of time, the scaling up and the scaling down design parameters will come into the picture. This is how we started our so exhaustive innovation using, okay. Whether still exploration related to its application to be made by Dr. Bhaskar. Yes, obviously we are in the process of working more into the exploration point of view. See, actually, one major thing with respect to sea exploration, I would like to say is like power is going to be a major hindrance for it. So what happens is this power capability, if I try to look into it, like in an underwater condition, tapping the power will be a difficult. So that is why now we are going to go for a piezoelectric structure, so that these piezoelectric structures can be appropriately maintained in such a way that you can tap power. Second most important thing, like people are worried about the environmental aspect, because in the case of seabed, when these systems go off, it is very difficult to track it. So basically, it should have a capability to get deteriorated in the sea. So we need to select the material which easily gets deteriorated in the sea. So that is why we are going for biodegradable piezoelectric structures.
Sir, I have one question, sir.
Yes, sir.
So you made a 3D printed fish head, no, sir? Whether it is a filament based material or a SMA, sir?
Actually, this fish head was made out of filament based material. Okay, so in fact it was a VLA based material, so that it has a very less density and it will somehow have a very good compatibility with respect to my buoyancy. So that's what we chose.
So any other question from participant side? Okay, so no question from the side. Okay, sir. So thank you for accepting our invitation and your enthusiastic and energetic presentation.